Hello, good morning. This is Professor Grenfell once again with another lecture for Math 12 Statistics. And today we're still working in Chapter 11, Section 2. This chi-squared test is going to be a test for homogeneity of proportions, which is weird to spell. But basically what this means is we're trying to determine whether proportions within a number of categories are approximately equal to one another or not. All right, so in this example, we're going to look at example 11-7, which is to see if there is a difference between happiness and income, or if the level of happiness, the proportion of people who are, quote, very happy, and the income category that they fall into are the same across these categories, or if they are different. So homogeneity means they're all uniform, and non-homogeneous would be there's differences amongst these categories. So here is the example. Here is the research scenario. It says a psychologist randomly selected 100 people from each of 4 income groups and asked them if they were, quote, very happy. For people who made less than $30,000, 24% responded yes. For people who made between 30,000 and let's just say 75,000, just for the sake of simplicity, 33 responded yes. For people who made between 75,000 and 100,000, 38% responded yes, and for people who made 100,000 or more, 49% responded yes. At alpha equals 0.05, test the claim that there is no difference in the proportion of people in each economic group who were, quote, very happy. All right, so the first thing that I'm going to do is organize this information instead of in a giant paragraph. We're going to put it into a contingency table. So across the top, I've listed the income groups. I've just abbreviated these for the sake of simplicity. Notice that this one is technically between $30,000 and $74,999. So it's, just less than 75, but we'll just say 30 to 75K, 75K to 100, and over 100K. All right, so those are the 4 categories, and we're going to test to see whether the proportion of people who are very happy is uniform across these. So let's see, in each of them, they asked a total of 100 people in each of these income categories. I'll just go ahead and write in the totals there. There's 4 income categories, so this total across this row should be equal to 400. And then, this makes it easy. Because we're dealing with percentages and not the raw number, we have to technically convert these into the actual number of subjects who are either very happy, so we'll just indicate that by checking yes, or not. So we'll just say no. All right, are you very happy? Yes or no. And 24% of 100, simply enough, is exactly 24. And so the no category here would be, well, let's see, if 24 out of 100 are very happy, then 76% would be the rest of that 100%. And so 76 individual people would have said no. Similarly, here we had 33 in this category, so that means 67 no's, 38 happy, and what's the difference? 100 minus 38, come on, you can do this, okay, is 62. I was talking to myself there. I have trouble with subtract sometimes. And here we had 49% happy and 51% not. Okay, and I left a little bit of space in each of these columns because we're going to go ahead and put the expected values just in the green right there. I'll go ahead and erase them for now so that we can fill them in later. Okay, and then we'll go ahead and take the row totals here. So grab my calculator real quick so I can do this while I'm speaking. So we've got 24 in the top row plus 33 in the second column. I'm just adding up all of the values in the top row here. And I got 24 plus 33 plus 38 plus 49, and that's equal to, I'm getting 144. Oh, let's take these little annoying pluses and equals out, and we'll just say 144 right here. And then similarly adding up what? The bottom row, 76 plus 67 plus 62 plus 51 equals a grand total of 256. And notice with any contingency table, we should have the last column also work as well. So the totals across this last column should be equal to the grand total of 400, and the total across this row, the total of the totals, should be the same whether you add up the columns first and then add up the rows, or add up the rows first and then add up their columns. You should get the same result either time. All right, so to see whether these income categories have uniform or homogeneous proportions of people who are happy versus not happy, we will now compute the expected values. All right, so if we're claiming that there is no difference between these, then what we can do is simply take the total number of people in each category, which in other words is the column total for each one of these. And this is kind of nice because it's 100 in each of these cases. And then to get the expected value, we'll multiply that by the row total for each one of these. So if I'm looking at this first value here, I'm going to take its column total times the row total and multiply those together, and then divide, of course, by the grand total. Okay, so we'll do that in each of these cases, and notice that the column totals are the same in all of these, for all of these expected values for the proportions. And so basically we'll be multiplying by 100 in each one of these cases. So for this first one, we're going to be multiplying the, so which first one? For this first one right here, we're going to be multiplying its row total times its column total. And I'll just cross that out for the moment. Multiplying 144 times 100, and then dividing by the grand total, of course, 400. And so that gives us 36. Okay, moving on to this next one. To find the expected value, we have the observed value. To find the expected value, we'll multiply its column total, or sorry, its row total times its column total. But notice that the column total is the same each time. So all of these are going to be multiplying by 100. And notice all of them are in the top row. So we're going to simply be multiplying the row total for the top row times 100 every single time. So 144 times 100 and then divide by 400. That gives us the same result of 36. And that's going to be the same in each of these. So basically, notice this. We're saying that all of these proportions are the same. Okay? Similarly, for this value, I'll just keep it in green, or write it in green. We're going to be multiplying 76 plus 67 plus 62 plus 51, which is 256, times 24 plus 76, which is 100, right? So the row total times the column total will give us the expected value for that particular observed value. Okay, and so that result, 256 times 100 divided by the grand total, 400, that gives us, we can easily see that that is 74. Okay. Oh, no, sorry, I did that subtraction wrong. I did that multiplication wrong. That should be 64. So notice another thing here is once we've computed the proportion of people who are happy, 36, we can simply subtract that away from the total, and that should be equal to this value. So that's how I was double checking that. Make sure my arithmetic is correct. I was actually doing the subtraction instead of the multiplication and division. And subtraction is hard for me for whatever reason, so I got that wrong initially. All right, so if these proportions of people who are happy, quote unquote, very happy, across each of these four categories of earning are the same, we would expect 36% to be happy in each one of these cases. All right. And in fact, that's exactly what we're going to say for our initial hypotheses. The null hypothesis is going to say the proportion from category 1 is equal to the proportion from category 2 is equal to the proportion of people who are very happy from this third income class of 75 to 100K is equal to this fourth one. And we could even say that this is, well, we've calculated the expected value, and that is equal to 36%. But regardless of what the expected value is, you don't have to necessarily calculate that ahead of time. In this particular case, they said test the claim that there is no difference. And so here we're saying they're all equal, and that is our claim. Keep in mind, a lot of the time, the alternative hypothesis is usually the claim. In this case, it is not the claim. All right, and the alternative to them all being equal is at least one of them is different. So I'll just say at least one differs from the others. They could all be different, you know, the top three could be the same and the bottom one could be different. You know, there's multiple different possibilities. So the most uniform way to negate this statement that they're all equal is there's at least one that's different. Okay, does that make sense? Yeah, I agree. That makes sense. Okay, now the next thing that we're going to do in our hypothesis test is the same thing that we always do in a hypothesis test. We're going to find the critical value, sketch the critical region. The first thing that we need to do to find our critical values for the chi-squared distribution, here it is, our chi-squared distribution kind of looks like that, is to determine the degrees of freedom. And so here the degrees of freedom are going to be calculated by the number of rows minus 1 times the number of columns minus 1. And so this is just going to be equal to 2 minus 1 times 4 minus 1. Why? Because, well, there are two rows, the yes, no row and the no row. That sounds weird. And then there are 4 columns, the income designations, these 4. So that gives us the degrees of freedom is equal to 3. And using our chi-squared distribution table, we're looking at the critical value so that the alpha is equal to 0.05 and degrees of freedom equals 3, alpha equals 0.05. The value that I'm seeing here is 7.815. And now we're going to move on to step 3, which is to calculate the test statistic. And here chi-squared is going to be equal to the sum of O minus E squared, all divided by E. And so I'll just go ahead and write down what, not E minus O minus E squared over E is for each one of these cells here. So for every one of these, I'm going to take O, subtract away E, and then square that, and then go ahead and divide it by E again. And we're going to do that for every square here. So we're going to see 1, 2, 3, 4, 5, 6, 7, 8 values there. So this first one is 24 minus 36 whole quantity squared divided by 36 plus 33 minus 36 whole thing squared divided by 36, and so on and so forth. And I should mention that we're calculating chi-squared, which is the sum of all of these values. So I've written on the whole top row, now continuing down to the second row, we had 76 minus 64 whole thing squared divided by 64, now is the expected value. Next cell is 67 for the observed value, minus 64 for the expected value, all divided by, well, all squared, and then divided by 64. And at the end of the day, we add all of those up. I'm not going to bother writing down what each intermediate value is because I'm actually using a spreadsheet to type everything in and do the calculations for me and then sum it all up so I don't lose any accuracy or a small degree of accuracy. And we'll round this chi-squared value to 3 digits after the decimal point in all of these cases. So we do that work to calculate the test statistic, and that came out as 14.149. Step 4, we'll go ahead and make the decision, and 14.149 is greater than 7.815, of course. And so notice here it's inside the critical region, and so therefore we reject the null hypothesis. And then in step 5, we say there is enough evidence. So remember, anytime you reject the null hypothesis, H subscript 0, then you have found significant evidence. So you always say there is enough evidence if you reject H subscript 0. And here, since H subscript 0 was the claim, you say there's enough evidence to reject this claim, that there's no difference in the proportions. You could also say there is enough evidence to suggest that there is a difference in these proportions. So if that double negative in there, not enough, there is enough evidence to say that there is no difference. You just say there is enough evidence to say that there is a difference, right? So instead of thinking about the claim and which one it is, I mean, the bottom line is you want to summarize the conclusions. And so here, since there is, or there seems to be, we found evidence that there is a difference in these proportions. What does that mean? That means that the income seems to make a difference in the proportion of people who are happy. And so that concludes example 11-7. on testing the homogeneity of proportions.